Let me try again. There we go. Okay, so I'm going to give you a brief introduction to electrochemistry, because I don't believe that anybody here is particularly involved in electrochemistry. And then I'll discuss the methodology that we use to study the structure at the electrochemical interface. And I'll try and illustrate that with one example, which is a little bit old, but is a nice example of linking structure and reactivity. And then I'll focus on the last point for the body of the talk. So we always like to start off with reasons why you should study this, and this is usually aimed at the funding councils. And of course, the nice thing about electrochemistry is there's a wide range of applications in electrochemical energy technologies. For example, hydrogen fuel cells, lithium-ion batteries, supercapacitors. All of these involve reactions that are occurring at the electrochemical interface. And plus, there's other areas as well. For electroplating is now used, as I'll show you in a minute, in the electronics industry. And there's sensor applications amongst several others. So there's a wide sort of interest in utilizing the electrochemical interface for a number of different areas. Okay, so oh wow, that's dated today. So this is a very up-to-date talk. Okay, so let's have a look at a couple of those as examples, right, to set the background. And this is an area that I've kind of worked in for many years, although I'm not going to really talk very much about this today. And this is it's in hydrogen fuel cells. So here's a schematic of a hydrogen fuel cell where your fuel is hydrogen. You split this on the anode material into the hydrogen ions and the electrons. The electrons then power whatever you want to power, and you recombine on the cathode side with oxygen to make water. So if you ignore the production of hydrogen in the first place, that's a very clean energy source. Okay, so the areas that we're interested in particular have been on developing the anode catalyst and the cathode catalyst materials. So initially, the interest on the anode side was in identifying impurity tolerant catalysts that don't become poisoned by side reactions, and the interest, but that's kind of been solved partly by the switch to using fairly pure hydrogen as a fuel. And on the cathode side, it's a good catalyst for this oxygen reduction reaction. State of the art is platinum nanoparticles, which still has many drawbacks. So it's working. So the work we've been doing there is on designing catalyst materials to improve efficiency in these devices. Okay, the other example I mentioned was electroplating, and in particular, this is a schematic of copper electrode deposition, which is used in the electronics industry. So forming these interconnects is done now by electrodeposition methods. And one of the interesting stages here is to get uniform filling of trenches in this electroplating method. So what you actually want to do, if you're depositing metal here and into some sort of trench, then you don't want the creation of these voids or sort of defects within the formed metal. And so the way to do that is to use additives of some form. So you want some catalyst to promote growth in the channel and some suppressor to stop the growth around here during the electroplating process. And if you get that right, then you can form a defect-filled trench by electrodeposition. So there's interest here in what the effect of various additives can be on these essentially plating type reactions. Okay, so that's two examples to try and convince you that it's worth studying, and that if you carry on, you may have at least some tenuous link with industry, which is always good. So let's get down to the sort of nitty-gritty and say, well, what are we actually looking at? And so this is a schematic of the electrochemical interface, which is sort of at the heart of all of these processes. So what's shown here on the left-hand side, we have some charged substrate, if you like, or material, which is our working electrode. In all of the work I'm going to describe, this is going to be a metal, but it could be anything. In fact, a couple of weeks ago, I was looking at uranium dioxide with sort of applications in the nuclear industry to understand corrosion. So, and it can be a semiconductor as well. So it has to be some sort of conducting substrate. And then on this side of the interface, this is the solution side of the interface. So these little things which look a bit like Mickey Mouse. These are water molecules. Okay, so I'm going to focus in this talk on water-based electrochemistry. There are other kinds, of course, but we're going to focus on water-based electrochemistry. So we have water floating around on the electrolyte side, and then we can have other species, for example, cations or anions. So cation shown here and an anion shown here, and when they're in the solution, they'll be fully hydrated. Now, depending on the certain conditions, you can break that hydration shell, right? We're going to apply a voltage across this interface. You can break that hydration shell, and then the anion in this case will become specifically absorbed, right? Will form a chemical bond to the substrate, and this forms the sort of closest approach of a specifically absorbed species, forms what's called the inner Helmholtz plane. Okay. Now, if you take the closest approach of a hydrated species, that gives you what's known as the outer Helmholtz plane, and this is basically what's known as the electrochemical double layer. Okay, so it's the double layer formed at the interface between the solid and the electrolyte. So, of course, in a plating process, you'd be breaking the solvation shell on the cation and depositing metal onto the surface. That's effectively the electroplating process. Okay, so aside from the sort of technological point, there's a lot of fundamental interest here. It's a bit of a playground, right, to explore different surface physics and chemistry. And that's what got me interested in it, because when I went out to Berkeley, as Peter said, I was working mostly with ultra-high vacuum equipment, and that's those of you who've worked with ultra-high vacuum know that you spend a lot of time doing nuts and bolts on a big chamber, and electrochemistry offers a way to do much of this kind of surface science a lot simpler, in a lot easier fashion, just in a plastic electrochemical cell. So that's what attracted me to it, and I've been working in electrochemistry now for coming on to 20 years. Okay, so why is it so interesting? Well, it's rich, right? There's a very rich, if you like, surface science involved in electrochemistry. So this is a very simple example. We can take a platinum crystal, so instantly you may think, oh, well, yeah, now I know why he was mentioning fuel cells. Right, you can take a platinum single crystal, a 111 single crystal, and you just dip it in some electrolyte. So we have typical, a kind of electrochemical cell here, where we've got an anode and a cathode, and we're applying a voltage between them. So it's like in a beaker. But if you do that and you measure the current as a function of the applied potential across the interface, then you can see there's lots of features. This is known as a cyclic voltammogram, and so we measure the current as we go around this way and then sweep the voltage back down again, and we can associate all of these features in the current with physical processes that are occurring at the interface. So even though this is just a single crystal of platinum in a very simple acidic solution, there are all these different phenomena going on in this cyclic voltammogram over a range of 1 volt, essentially. So we're just applying 1 volt across the interface. Of course, the field strength across the interface is 10 to the 7 volts per centimeter or something, but it's 1 volt applied across the interface. So the process is here. The negative current here is essentially where we're breaking the water and getting the evolution or production of hydrogen gas. That's at the sort of negative limit, and that defines the negative limit of where we can go. Then as we sweep more positive, we have current here, which is associated with the absorption of atomic hydrogen on the surface. We then have this very pretty feature in here, which was known as the butterfly feature for a while, and this corresponds to the absorption of sulfate and desorption of sulfate, and then also the absorption of OH from the solution. And then you go into a sort of stable region where you're just charging this double layer. If you went a bit more positive, you'd reach the potential for oxidation of the platinum surface. Okay, and that defines effectively, and if you went beyond that, you'd go to oxygen evolution or production of oxygen gas. So that defines the potential range that you can sweep over. Okay, so it's very rich. Even for a very simple system, you have a lot of interesting things going on. Okay, so we need to have a look at that. So we want to probe what's going on at that interface, and that's where the difficulties come, right? Because as a surface scientist, you know, you're used to having some kind of substrate with some atoms on, and then you can go and use your full range of electron-based, typically, techniques to have a look at what's going on with the arrangement of atoms. Now, the problem is, of course, we have the water layer on top. So you can throw away all your electron-based techniques because you can't get in and out of the electrolyte solution. You know, in the gas phase, you can control pressure and temperature, whereas in the electrochemistry, the equivalent of those, if you like, the equivalent thermodynamic parameters are the applied voltage, and there is some equivalence between the two. So how do we probe this? Well, there are kind of two principal methods. One is what I call a brute force method. You can bring an STM tip right through the liquid, and you can image what's going on the surface. Or the technique that I favour, the more gentle technique, is we're going to use X-rays to scatter. The X-rays can penetrate through the liquid layer, and they can scatter from the surface, and then they can penetrate out again, and we can do a diffraction type experiment. So that's the one I'm going to focus on. Experimentally, how do we do that? Well, we need a specialist sort of electrochemical cell, and this has been the workhorse design that we've been using for 20 odd years now. There are other ways of doing it too, but this is a schematic of the sort of workhorse design. We have our electrode, which is sat in the middle of this cell with a connection to the back. So we're forming an electrical contact through the back. We then have the electrolyte which comes over, and we have two other electrodes going into this electrolyte, a reference electrode which has a standard drop to the solution, so that when we measure voltage, we're doing it with respect to a known standard. And then we have a counter electrode, which is what the current flows between the working electrode and the counter electrode. Okay, so this thing works in a couple of ways. We have a polypropylene film, or it can be made of any kind of plastic. It has to be sort of invisible to the X-ray beam, essentially. And then when we want to do the X-ray measurements, we can collapse this film down onto the surface, and it will trap a thin layer of electrolyte, but we still maintain electrochemical contact. So we can still do electrochemistry. It's just in a thin layer cell. And in that situation, we can bring the X-ray beam in and out, and it's not too attenuated so that we can measure our signal. Okay, what does that thing actually look like? Well, here's one in action. It's real science, you know. It's got tape wrapped around it and all kinds of stuff, right? Especially our version of it. So this is the electrochemical cell. It's about that big. Okay, across. The crystal in there is a gold crystal. That's our working electrode, and that's about 1 centimeter in diameter. Okay, so you can see the O-ring, which is sealing the polypropylene window. Okay, so this is actually sat on the diffractometer, and you can see the inlet and outlet for the electrolyte, and the crocodile clips are making the electrical contact to the various electrodes. So that's what it looks like, and then of course you've got to stick that on a beamline. Here's my favorite, as Peter mentioned. This is the Xmas beamline, currently shut down in Grenoble, and And the nice thing about this beamline, the sample now is sat at the center of these diffractometer circles. We're enclosed it in a capped-on hood so that we can protect from the oxygen in the atmosphere, basically. So that's filled with nitrogen. And the surface is pointing in this direction. And the beautiful thing about this diffractometer, it's very versatile, right? As anybody who's worked there knows, it's an 11-circle diffractometer. And it means we can do our surface diffraction experiments in a number of different ways. In particular, well, I'll come on right towards the end of the talk, we can control the orientation of the surface with respect to the polarization of the incident beam. So the incident beam's coming down here and is polarized in the horizontal plane. So by changing the way we do the diffraction, we can control the orientation of the surface, also with respect to the polarization of the beam. Just a quick plug for those of you who don't know, if you want to use the beamline, it's funded now until 2000 and, actually it doesn't say on there, but it's funded until 2017 if we're allowed to reopen after the latest safety calamity. And you know, it's a general materials beamline for diffraction type experiments. So if you think you might have something that fits in as interesting, just let me know. It's open access for UK users, basically, so it's an easy way to get into the ESRF in these difficult times. Right, let's get to the measurements. I'm probably talking to people who already know all of this, but I'll remind you anyway. What do we actually measure? What are we measuring when we're doing surface diffraction? Well, essentially, we're measuring the Fourier transform of real space. And so if we take the example of a monolayer of material, then in the reciprocal lattice, which is where we do our X-ray measurements, this would give rise to rods of scattering, right, which would be extended completely along the surface normal direction. If we have the surface now on a crystal, right, then we're going to have Bragg reflections as well as these rods of scattering, and these are shown by the sort of points here on these rods. So we're going to have the rods and we're going to have the Bragg reflections due to the scattering from the bulk of the crystal. And then this can interfere as well in some way and be modulated along this surface normal direction. And this has become known as crystal truncation rods after a bit of early debate about what they should be called. Okay, so this is effectively what we measure in the experiment. Let's go to a specific example and see how, because what we want to do at the moment, right, we're talking about the X-ray measurement. We want to see how we can marry it into the electrochemical experiments. So if we take a specific example, we take an FCC, and I'm going to focus initially on platinum, right? If we're going to take an FCC 111 surface, then here's a schematic of the real space. That's the top view of the hexagonal surface, and the side view showing the ABC stacking. Then in the reciprocal space, that gives us a hexagonal surface plane, and then these rods of scattering extend along the surface normal and pass through the bulk Bragg reflections, which are shown here. Okay, now we use, in surface diffraction, we always use a Miller notation where we have L along the surface normal, even though it's a 111 surface normal in this case. So we just make a transformation. Now, so this is what you would get if you just had your platinum crystal. Now, the interesting thing is, if you do something to the surface and you generate some structure which has a different symmetry, for example, if you had something with a 2x2 symmetry, or a larger symmetry than the underlying crystal, then that's going to give you scattering in the reciprocal space, which is separated from the scattering due to the platinum crystal. So that would give you rods of scattering basically at the half integer positions if you had some structure with that symmetry on the surface. And this is really nice because the next slide shows an example of that, right? So I've jumped a little bit. So if you remember back to the a few slides ago when I showed you the cyclic voltammogram of platinum in a simple acid, you remember all those peaks and it correlated with different processes. Well, if you put carbon monoxide into the solution, then carbon monoxide absorbs on the surface and basically blocks all of those. And so the cyclic voltammogram you measure now looks something like this. It's called a polarization curve, and you only get current when you have oxidation of the absorbed layer of carbon monoxide on the surface. Now it turns out that the carbon monoxide actually orders on the surface. It orders into a 2x2 unit cell, which is schematically shown here. So here's the ordering. There's a simple unit cell with 3 carbon monoxide molecules in a 2x2 unit cell. And we can measure this with diffraction, okay, because it's separated from the scattering from the platinum, and we can measure it. We can measure the intensity, which is just due to the ordering in this layer. Now we can apply the voltage, we can change the voltage, and so now we can link the structural measurement with the cyclic voltammogram and combine the two. And we came up with the acronym of X-ray voltammetry, right, which has a nice XRV, sounds very flashy, high-tech, right? You always want a good acronym when you're doing science. And so we invented this term called X-ray voltammetry, and that's measuring the diffraction signal as a function of the applied voltage. And we can then compare that to the cyclic voltammetry and understand the changes in the atomic structure that are coupling in with the reactions that are going on the surface. So in this case, what we actually find is if we sit on this peak on the scattering, which is just due to this 2x2 structure, then as we cycle the potential, the structure disappears, and then when we cycle the potential back, the structure comes back. Okay? Simultaneously, it turns out that you'll notice this is before the onset of oxidation due to CO. Right? Oxidation due to CO is starting to begin here, but this structure is lifted before that. And what actually happens is it goes through a phase transition to a slightly different structure. It sounds very complicated. It's a root 19, right? And it has 13 CO molecules in it. But all you really need to know is it's just another hexagonal structure with a slightly larger lattice constant. Okay? And this gives rise, of course, to a different diffraction signal at a different place in the reciprocal space, which we can also measure. So what we find is when the 2x2 structure disappears, this root 19 structure appears, and then vice versa when we go back again. So there's basically a reversible transition occurring in here, right, due to the oxidation of a small amount of the CO. This is pre-oxidation before the main oxidation process. And you can actually see there's a little bit of current here which corresponds to that charge due to that oxidation. How can we understand that? Well, we can go back to UHV and we can look at the energy of absorption of CO on platinum, and we can see that it basically looks something like this. And when we get into this high coverage regime, which is the one we're in, up at around 0.75 here, 0.75 is actually not even achievable in ultra-high vacuum conditions. But basically, you can see that the energy of absorption drops dramatically. And so effectively, what we're doing, we have a pre-oxidation because the CO is in a weakly absorbed state when it's in this very high coverage state. And when we oxidize a little bit of it, it moves back up this absorption isotherm and then is in a strongly absorbed state and is more sort of tightly bound to the surface. Now, the power of X-ray diffraction is, I've shown you X-ray voltammetry, which is measuring the signal as a function of the applied potential. But of course, you can fix a potential and then go and do a full characterization of what's going on your surface. And that's been done, not by me, I might add, but for the strongly absorbed state, this root 19 CO structure. And this was published back in 2005, and there's dramatic restructuring of the underlying platinum associated with the absorption of CO in this state. So strongly absorbing it really is, because there's a very strong interaction then with the underlying substrate. So using a sort of full detailed X-ray diffraction analysis, you can pull out this level of information, and there's all kinds of rotations and relaxations and whatever going on in the underlying crystal induced by this CO. Okay, so that was my introduction. Hope you're still with me, because I'm going to move on to something. I'm going to focus the rest of the talk onto something else, okay, which is related but is not reactivity, if you like. And this is some work we've very recently been doing on structure, not just structure, but also charge transfer, trying to understand the influence of electrochemical environment on both the nature of the surface add layer bonding and in particular on things like partial charge transfer at the interface. Whenever you have an absorption process at the electrochemical interface, you have an electron transfer. That's the driving force of the reaction, if you like. But the question is it a full electron transfer? What is the charge distribution in the electrified interface? And it's important to know this. One of the reasons why it's sort of important is because we want to target structural modification with desired properties, and in particular there's a technique known as galvanostatic replacement. Okay, what does that mean? If we take something like a core shell nanoparticle, right, which are finding increasing applications in a wide variety of technologies now, in a core shell nanoparticle we have some core of a metal, for example gold, and then we form a shell on the outside of, say, another metal, copper. And by tuning, this effectively tunes both the strain and the electronic surface properties and will give us particular reactivity towards specific reactions. Okay? Now the galvanostatic displacement method is a method whereby you use a sacrificial layer which can then be replaced, because at the electrochemical interface you're in chemical equilibrium, and so a displacement reaction can occur if it's energetically favorable just by changing the solution, right? Even without applying a voltage. So anyway, so the question is, how can we learn about this process? What can we learn from single crystals about how these processes might occur, how we might improve them, and actually the fundamentals of, why do they even happen, right? So going back to the nanoparticles for a moment, I'll notice that characterization of nanoparticles is mostly done by X-ray absorption spectroscopy, and there's a lot of ambiguity in determining whether the contributions in that spectroscopy are surface or bulk contributions. So I'll hopefully show you a way around that using diffraction at the end of the talk. Okay, so this links back to the sort of deposition type experiments that I mentioned earlier. What we're going to focus on is we're going to look at a couple of metals, gold, in particular gold and copper. And now I've switched, they're still FCC metals, obviously, but now we're going to look at the 100 surface, the square surface of these metals. And our aim is to understand the bonding mechanism and charge transfer in metal halide systems. So by halides, I'm specifically going to talk about chlorine and bromine. Right? Quite often these are in solutions and can be used as kind of suppressors or catalysts for deposition processes. So what we want to do is find out what's the influence of the halide anion on UPD. It is just a deposition process, okay? UPD is actually short for underpotential deposition, which is the deposition of one single monolayer of a metal. We want to, the sort of physics is interesting. When we deposit a metal monolayer, how does that system behave? Because that's effectively now a core shell type nanoparticle. If we deposit one monolayer on a surface, we're effectively mimicking the situation that we have in a core shell nanoparticle, where we have a monolayer of material on a different shell. And so all of these factors are going to influence electrochemical function, right? This is why we want to do it. And as I said, we're going to focus on one simple surface geometry. And the reason for doing that is because the structures that we're going to form have very simple absorption sites. This is something we learned the hard way when we tried initially to do these experiments. That will become clear in a moment. Just a quick note here that when you put bromine onto gold or onto copper, right, then in the case of on gold, we actually form a hexagonal structure, and on the case of copper, we're going to form a square structure. I'll explain that in a minute. Right, so let's look at our reciprocal space, real space thing again. Okay, so now we're looking at the square surface. Right, so our reciprocal space is also square. We have our truncation rods now going through these various Bragg reflections here. Right, so this is what we can measure. And then what we find when we put chlorine or bromine on this surface, chlorine and bromine are slightly much larger than copper, so they can't be commensurate, if you like, with the lattice. But what they tend to do is actually just form another square structure, and in this case it's known as a centered 2x2 structure, so it's slightly larger. That's due effectively to the radius, atomic radius of the halide anions. And that of course gives rise to scattering again, which is separated, right, in the reciprocal space from the scattering due to the underlying copper. So we can measure that independently. Okay, so that's been done, right, and here's actually a couple of measurements along one of these superstructure, what we call superstructure rods, right. So that's looking at the L dependence, the dependence of the intensity along this rod. Now, if it was just a single monolayer, if it was just corresponding to these atoms in the surface layer, then it would just have a decrease according to the form factor and any Debye-Waller type factor. But what's actually found is that it oscillates. Okay, so the intensity oscillates when we look in the L direction. So the topmost measurements were measured in ultra-high vacuum, and the lower measurements were measured in electrolyte. And so in both cases you can see an oscillation, right? And from the oscillation, that tells you something about the thickness, if you like, of the atoms that are contributing to this scattering. And it turns out that by symmetry it has to be the second copper layer, right? Not the surface atomic layer, but the one underneath. And what we find is that if you look here, the oscillations are in antiphase between the two different situations, right? So if we're in the UHV environment or we're in the electrochemistry environment, then these oscillations are in antiphase, and that can kind of be understood by the buckling of this second layer, which is kind of exaggerated here. But here you can see the atoms are buckled in this layer, and in fact between the ultra-high vacuum and the electrochemical situation, that buckling is reversed. That's why you have the antiphase. Also, the bond length seems to be more covalent in the case of ultra-high vacuum, but is closer to the ionic bond length that you might explain in the electrochemical environment. Okay, so if we switch now, we're going to combine all of this in a second, but if we switch now to the case of the halide anions on the gold surface, then as I said, they actually form a hexagonal structure, which is shown here, and this has a slightly different symmetry. It's what's called a centered 2√2 by √2. Okay, but again, that gives rise to scattering. We can measure that as a function of the applied potential, and we see ordering into this structure, and then at higher potentials it disappears, and that's fully reversible. And so if we focus on that, then it appears, this is all done in the electrochemical environment obviously, then we can sort of solve the structure by looking at the detailed scattering in the truncation rods and the superstructure rods, and we find a bond length then again which is closer to covalent bond. Now the interesting thing is that the coverage by the anion species here is half a monolayer, which is the same as the coverage on the copper surface, and yet the structure that's formed has a completely different symmetry. Right? So it's hexagonal on gold and it's square on copper, and yet the coverage is identical. So the question is then, what if we combine copper and gold and we modify the gold surface by depositing a monolayer of copper? We can do this electrochemically. What do we find then in a system? So all we're doing there's a whole variety of experiments here. All we're doing is changing the solution, right? It's that simple. This is the beauty if you've ever worked with ultra-high vacuum. In electrochemistry, we just syringe out the old solution and flow in the new solution, and you're doing a completely different experiment. Now, in this case, we have copper in the solution, and so we can deposit copper. We still have the halide ions. Now, what happens, what's shown here is our so-called X-ray voltammetry measured at two positions, one where we're scattering from this square structure and the hexagonal structure. These points are actually equivalent, and the lower one is just scattering from the square structure. Okay, so what we find is, on gold, we form this hexagonal structure, right? The blue line is actually the negative sweep. So we form the hexagonal structure, it then disappears, and this we can correlate with the onset of copper deposition. Surprisingly, it reappears for a while, and then it disappears completely, and then at very negative potential, we actually form another structure again with that kind of symmetry. If we look at the scattering from the hexagonal structure, it's pretty similar in this middle range, but there's nothing formed here, and that tells us that actually at the very negative potential limit, we're forming the square structure of the halide anion on top of a copper monolayer on the gold substrate. Okay, and we can do our detailed characterization of that structure, and then we find that, again, we're closer to this ionic bond length for the copper-bromide interaction. We have the same relaxation process that we found on a pure copper crystal, and yet now we have only a single monolayer of copper and gold underneath, and yet the gold atoms behave almost identically to those of the copper atoms when we have a copper crystal. So it appears that one monolayer of copper is effectively enough to act like a bulk copper crystal as far as the anions are concerned. Right, it's quarter. How much longer would you like me to talk? 5 minutes?
Yeah.
Right, okay. So basically, okay, so this is a brief summary of what I've saying. Basically, at negative potentials, we have this square structure, and everything's consistent with partial ionic bonding or some form of ionic bonding. Now, of course, this is all indirect, if you like. We're inferring the nature of the bonding from the bond lengths, but that's not a direct probe. Right? Now, the big question is, is there anything we can do to access the nature of the bonding directly and to learn something about the charge distribution at the interface? And this is what led us towards resonant X-ray scattering, right, in which we're going to tune now. We're going to still be doing diffraction, just like I've been describing, but now we're going to tune the incident energy of the beam, right, of the X-ray beam through an absorption edge in one or maybe all of the materials that we're studying. Okay, so we're familiar with this. This is taken from Des McMorrow's book, which is just showing the dispersion corrections as you go through some absorption edge, right, which is modifying the atomic form factor according to in the standard way. So what we're effectively going to be doing now in our experiment is we're going to be looking at the diffraction, but we're going to be scanning the incident energy through an absorption edge in one of the materials or one or more of the materials that we're looking at. But we're going to maintain the diffraction conditions while we do that. Okay? So we're going to select effectively the atoms using the diffraction condition and then try and get some spectroscopic information from the resonant diffraction. Okay, so these are some of the first results. Okay, this is going to be the first set of data is scanning through the copper absorption edge. Okay, and this is in the case of the copper chlorine system. So we have a copper single crystal, the 100 crystal, and we have this square chlorine structure absorbed on the surface. And what we're doing now, what's shown here, as you can see, the data looks very much like the F prime, right, as we go through the absorption edge, and the energy of the edge is located here by this solid line. Now, all that's changed in these three sets of data shown, these are actually measured on one of these truncation rods. As we move from a condition here, 11.8 is near to a 111 Bragg reflection, and so we're scattering essentially from the bulk of the copper crystal. 110.2 is very close to a so-called anti-Bragg condition, and in the anti-Bragg condition, the scattering from the bulk of the crystal is entirely cancelled, and we're only sensitive to the surface atoms. Okay, and what we can see is as we move to this position, we can see a shift in the absorption edge, right? So it's shifted to higher energy, which suggests that we have stronger bound core electrons in the atoms that we're scattering from, or that the surface atoms possibly have some positive charge. Now we can do this on the superstructure rod. This data is a little bit noisier, purely because if you think about what we're doing, we're scattering from monolayer quantities of material here and trying to do resonant diffraction on them. So it's not an easy experiment. But you can see, again, now we're measuring along one of these superstructure rods, and at the position where we're nearly in plane is given by, if you focus on the blue line here, we can see there's a big shift away from the edge position. The intensity now goes up because the copper scattering is effectively in antiphase. So when we reduce the scattering power, we increase the scattered intensity. But you can see that we still have this large shift away from the edge. In fact, it's entirely consistent with the shift we measured in the last slide. But this shift decreases as we go higher up to a different position, and that's because of the tilting of the sample surface with respect to the polarization. So in this situation, in the blue case, the polarization is oriented along the surface normal, and that's the point where we're strongestly coupling in to the charge transfer across the interface. Okay, so there's a polarization dependence. So finally, we can go and look at the bromine situation, and this is my last but one slide, you'll be pleased to know. Finally, we can look at the bromine situation. We can look at the scatter through, do the resonant diffraction through the bromine edge. Right? So the previous measurements were done on the metal edge. We were probing the state of the metal atoms. Now we're looking specifically at the bromine atoms. And when we, okay, so now this is the example of bromine on copper. And when we're fixed with the polarization of the incident beam again along the surface normal, so that we're coupling into the charge transfer, then we can see that there's a shift in the edge position, and now it's in the opposite direction to the shift that we observed with the copper atoms, okay, which is implying that our bromine atoms also are retaining a charge, a positive charge in this case, which is giving us the shift in the other direction. So this was a situation where we believed from the bond lengths that we had sort of some sort of partial ionic bond, and we can see now from the resonance scattering that we do indeed see a partial charge on the atoms at the interface. If we do the same thing with gold, where we were consistent with a covalent bond, then we see no shift. So it's a good test, right? Okay, so I think I've tortured you enough. That went from the basics to something quite complicated, and I hope that you got something out of it. Summarize, as I said at the beginning, you know, it's nice to work in electrochemistry. It's the time of electrochemistry now, particularly in energy-related issues. It's an important area. there's a lot to understand. We need to understand structure-reactivity relationships. And basically, there's a limited number of techniques you can use because you have to throw away all of your ultra-high vacuum-based techniques. I've tried to show you that surface diffraction is a good technique. It can give you both indirect information or maybe even direct information using techniques like resonant diffraction. And of course, I could give a whole other talk about non-aqueous electrochemistry. Just acknowledge the people who worked on this. Paul's been excellent at doing a lot of the technical development behind some of the electrochemical cells and supporting apparatus. There's a vast number of PhD students who've passed through and dipped in and out of these studies over the years. Yvonne's been central to some of the more recent work, particularly the resonant diffraction work. And Nenad and Voya are my collaborators who were originally in Berkeley but are now in Chicago. And we work a lot on the electrocatalysis side of things with them. And so, thanks very much.
Okay, traditional now for the audience to show how much it's understood of this talk by asking really dumb questions.
Well, you
want to start off?
Yeah. So, in your resonance scattering experiments, you showed the copper cage.
Yeah.
Air ledgers in transition metals are very good for looking at, say, vacancies, occupancies in the orbitals.
Yeah.
Is there experimental difficulties using copper L?
Absolutely.
It's completely and utterly impossible.
do you know what the energy is?
I thought in software you could do it.
Yeah, the air age. I also don't know where the air age is, but copper doesn't help.
900 EV.
900, right? Yeah, you can't. You can't do diffraction with 900 EV. Well,
we can.
And you won't get. Yeah, you can, but you're right. You won't get through the electrolyte either. The lowest energy we've ever used for doing these type of experiments, we once did an experiment on the tin edge, which is at 4.9 keV, and that worked. We were trying to probe the electronic state of tin in a platinum tin surface alloy. But that's the problem is, as you decrease even further your attenuation in the liquid, you have about 10 microns of liquid. But if you work out, with a path length of several, path length is not too much bigger because you don't tend to go in at grazing incidence. But even so, your penetration, as you decrease the energy, just goes. You lose all signal.
And plastic and everything.
Yeah.
Right. Can I have two questions?
Yeah.
It wasn't quite clear. Is your scattering geometry, are you doing in-plane diffraction or are you doing out-of-plane diffraction with the scattering plane?
Well, when we do, it depends which measurements. In general, we're not really doing any kind of grazing incidence diffraction. Because if you go right down to grazing incidence, you're going to have very long path lengths in the liquid, right? We tend to never work at grazing incidence. We're measuring always with several degrees or greater incident angle. Now, in terms of the geometry is important, particularly with the resonant measurements where we have to orient with respect to the polarization. So the way we effectively do that is we're doing, when we want the surface normal along the, when we want the surface normal perpendicular, parallel to the polarization, so it has to be in the horizontal plane, right? Then we're doing diffraction essentially in this vertical plane. But then we can change the experiment around and do diffraction in this plane as well, right? That's the beauty of the diffractometer. So we can work either with a horizontal scattering plane or a vertical scattering plane, dependent on which polarization we want to use. Now, of course, if you scatter horizontally, you start to lose signal as well.
But you always have you normally have the surface normal in the scattering plane.
No, not at all. It can change. Yeah, we do for probing the polarization effect. We want to align the surface normal with the polarization, so we do then. But in general, no, we don't. Yeah.
My second question relates to your platinum early example. You showed the signal change as you applied voltage, but it wasn't reversible. What happens if you do it again?
Which one? I know. You mean you're talking about the CO structure?
Yeah.
This one?
Yeah.
You mean it doesn't come back to the same intensity? That's a yeah, that's a very interesting case. Okay, there's some kinetics, right? There's also some kinetic processes going on. Right, this is done with a certain sweep rate. If you change the sweep rate, you'll find it might be fully reproducible. Right, so they're kinetic effects. The structural ordering can take time. Okay. Now the case you've hit on there is actually a very, very interesting one, because it turns out if you take a platinum 111 crystal, the way these are prepared is they're prepared in by annealing, right, in an inert atmosphere. You can either do it with a hydrogen flame or you can do it with another method, and then they're transferred into the electrolyte. And it turns out when you do that, you actually have many defects on the surface. Okay. CO, right, this is another beauty about electrochemistry. If you put then CO into the solution and you cycle over this CO oxidation, you actually will move the defect atoms around. Okay, and this is kind of well known, and even for other materials, you don't even need CO in there. Just by cycling, you're moving atoms around, and which has become known as electroannealing. You can effectively change your surface, or improve your surface, if you like, by moving atoms, moving defect atoms, and step edges, and all kinds of things, right, by electrochemical cycling. And in the case of CO on platinum, when you first start, you have many defects, and you'll find that your coherence length in your CO structure is quite small. With repeated cycling, it actually becomes much, much larger. Yeah. So these measurements will have been obtained after, say, 1 hour of potential cycling in CO, where you've effectively really improved the structural order of the surface by moving the defect atoms to step edges.
Are there any other questions? Okay, well, Chris is around for a few more hours before attempting to get back to Liverpool. It's nice to see an example of surface science, because surfaces are everywhere in real life, and unfortunately surface science techniques tended to be UHV dominated, have not actually had much impact, and this is a nice example where you can actually study real life surfaces under realistic conditions and get structural information. So, thanks Chris.